Alright, so following these experiments, he was able to define a new quantity which was called the Reynolds number, Re. Reynolds number is given by the density of the fluid density, the velocity of the fluid, the diameter of the pipe over mu, which is the dynamic viscosity of fluid. This can be rearranged to get the kinematic viscosity of fluid, Ni, which is given by mu over rho, times the diameter over the velocity. It's the velocity right here, times d over Ni, this is Ni, which is the kinematic viscosity of fluid. This Reynolds number defines all these three kinds of flow. So, for example, for small values of velocity, you get, and for small value of Reynolds number, you get the case of the laminar flow. And this is true for Reynolds number in circular pipe lower than 2300. When Reynolds ranges from 2300 to 4000, you get the transition flow, again in circular pipes, while when Reynolds is higher than 4000, you get the turbulent flow, again in circular pipes. So, let's try right now to define how to evaluate tau zero, because our aim is to define the losses, and the losses are related somehow to this tau zero. But to define tau zero, the real aim of all our study is to define the hydraulic gradient J. Hence, in general, tau zero is a function of the diameter of your, in the case of circular conduits, so it's the diameter, is a function of the diameter, of the relative, of the roughness of your pipe, of the velocity of the flow, of the dynamic viscosity mu, and of the density of your flow. In the case that you are considering any other kind of form for your pipes, you have also to add to this dependence also a shape coefficient. So, recalling the Reynolds experience, let's try right now to define for different kind of flow how to evaluate tau zero. The first flow that we are observing is the laminar flow, and in this case the tangential tension tau zero is a function only of the diameter of your pipe, of the velocity, and of the dynamic viscosity. It is possible to demonstrate, but we won't do it because it's just to give you the basic concepts. But you have to know that it's possible to demonstrate that from dimensional analysis you can get that the tangential tension in this case is given by K, a factor, times mu over g times the velocity. If you compare this one with the definition of tangential tension, which is again gamma times r times j, and in the case of a circular pipe, r is given by g over 4, as we demonstrated before, you can get exactly this expression for j. And let's try to do it together. Alright, so sorry. Alright. So we are talking about the condition of laminar flow. We said that from dimensional analysis, tau 0 is equal to a factor k, which is times mu, the velocity, over d. In the same way, so this is our first equation. The other equation is that tau 0 is given by gamma rj. So in case of circular pipe, it becomes gamma d over 4j. Let's compare this with this. We get kappa k times mu v over d equal to gamma d over 4j. And right now we want to get j. So j will be will be 4k mu over gamma then we have times the velocity over g. Let's bring it right here, so it becomes g to the power of 2. Alright, so if we observe this relationship that we get, we can observe that j is linked to the velocity at the first grade, so it becomes proportional to v. Recalling Navier-Stokes, which said that for laminar flow J is equal to 32 mu over gamma v over d to the power of 2. If we compare Navier-Stokes in laminar flow with this stuff, we can get that again this term mu over gamma times v to the power of d v over d to the power of 2 is equal to this stuff. So we get that 32 is equal to 4k, and k is equal to 8. As we can, for example, substitute this thing right here and get that tau 0 in laminar flow is equal to 8 mu v over d. So we have found the expression for the tangential tension in the case of laminar flow. Right now, let's try to define the same things for a completely turbulent flow in smooth pipes. Smooth pipes are, of course, ideal pipes where the roughness is not relevant. In this case, it's possible to demonstrate that tau 0, the tangential tension, is a function of d, the diameter, the velocity of the flow, and the density of the flow. Hence, from dimensional analysis you get this stuff, so tie 0 is equal to lambda 1 times rho v to the power of 2. Again, you compare this thing with this one, and let's see that exactly as the previous case, we can get an expression for J. So, let's go back to our paper. Again, if I don't make any disaster. Hope it is visible. Alright, so we get the demonstration for the laminar flow. We do the same for the other case, which is again completely turbulent flow in smooth pipes. Hence, again, from dimensional analysis, we get that tau 0 is equal to lambda 1 times the density rho times v to the power of 2, but at the same time we have to take into account that tau 0 is defined as gamma r j, so it will be gamma d over 4 times j. Let's compare these two. We get that lambda 1 rho v to the power of 2 is equal to gamma d over 4 j. From this equation we find again j, so j will be equal to 4 lambda 1, again rho over gamma, v to the power of 2 over d. So in this case, but gamma is rho times g, so it becomes 4 lambda 1, the density rho over the density times g, so it's possible to erase them, times v to the power of 2 over d. And finally it is equal to 4 lambda 1 over g times v to the power of 2 over d. Hence, as before, we can observe that j is equal exactly to v to the power to a factor times v to the power of 2, so it's proportional to v to the power of 2. Commonly, it is possible to say that, let's try to take another paper, let's try to see if it's alright. Yes, it's almost quite visible. Okay, so if we commonly we can say that for this case lambda we define the factor, so this is Gauling, we can see that there's a factor lambda which is equal to 8 lambda 1. This factor lambda is our friction factor. So basically we can say that if lambda is our friction factor, for lambda 1 we can just rearrange this stuff and get that J is equal to lambda over D times v to the power of 2 over 2G. This thing right here is Darcy-Weisbach. So it's a law which is called the Darcy-Weisbach law, and it's valid for every kind of flow because it is considering turbulent flow in smooth pipes. So basically we will see that when you don't know anything about the nature of your flow, so you don't know if the flow is laminar, if the flow is a transitional flow or a turbulent one, you can, to compute the hydraulic gradient and consequently the distributed losses, you can use this stuff, which is called again Darcy-Weisbach. And in particular, let's observe that this stuff see a dependence of J from the friction factor lambda. So it follows that to know J, to know your hydraulic gradient, you must know the friction factor. And this friction factor, we will see in a while, that depends exactly on the nature of your flow, so on the condition of the motion of your flow, so if it's laminar, if it's transitional, if it's turbulent, and according to the kind of regime of your flow, it depends again from only the nature, both the nature and the geometry, and only the geometry. Alright. Okay, so let's observe one thing. If we recall the laminar flow, we can define a tangential tension for the laminar case, which was from the dimensional analysis K times the viscosity, dynamic viscosity mu times the velocity over the diameter. The same is true for the turbulent flow, which is given by, from dimensional analysis, lambda 1 times rho times v to the power of 2. Just making a ratio among these two quantities, you can get that tau 0 in turbulent case over tau 0 in laminar flow is exactly this ratio. Alright, so it follows that it's proportional to rho v d over mu, which is exactly Reynolds number. So a way to define your degree of index of turbulence is to make a ratio among the stresses in laminar flow over the stresses in turbulent flow over the stresses in turbulent flow. This ratio is also called the turbulence index. Another very important observation is that if you just recall the Darcy-Weisbach laws that we have defined before, and if you consider, since this law is valid for every kind of flow, if you consider the laminar case, so it's valid Poiseuille law, which was again 32 mu over gamma times v over d to the power of 2, just comparing these two things, you can get that lambda is equal to 64 over Reynolds. Hence, let's try to see if it's true or not. So, let's go back to again our paper. Alright, so for example, we want to compare this thing right here with this thing right there. So it's a particular case, and this particular case is that just it comes that 32 mu over gamma times v over t to the power of 2 is equal to, again, lambda over g times v to the power of 2 over 2g. Alright, so we want to get lambda. We can simplify lots of things. For example, this v is erased with this one, this g is erased with this exponent. So we get that lambda is equal to 2 times 32 comes to 64. Then it is mu times g over gamma d times v. Remember that gamma, again, the specific weight is the density times g, so this is 64 times mu g over rho g times v times d. Hence 64 times erase, it becomes mu over the density, velocity, the diameter. But this stuff right here is the inverse of Reynolds, so this is 64 over Reynolds. These first things right here that we get just comparing Darcy-Weisbach that we obtain in case of completely turbulent flow in smooth pipes, but it's again valid for every kind of flow. Just comparing this one with Navier-Stokes in laminar flow that bring you to these things that is Poiseuille law, allows you to define for a laminar flow the first resistance law. So what can we say? We say that if we are in laminar flow, your lambda, which is the friction factor, is totally dependent only from Reynolds number, which means that it is defined by only the nature of your flow. So its density, its velocity, the diameter of the cross-section that is encountering, and the dynamic viscosity of your flow. Alright, so let's go on. And let's try to define the third case, which is the transition flow in smooth pipes. So in this case, the tangential tension is a function of the diameter, the velocity of the flow, the density and the dynamic viscosity. Again, from dimension analysis, you can get that tau 0 is equal to the density times the velocity to the power of 2, so it's exactly like the turbulent flow, if you remember, but there's also another kind of dependencies, because instead of the turbulent flow, that from dimensional analysis you got these things, so it's lambda 1 rho v to the power of 2 and lambda 1 was a constant. In this case, if you are considering the transition flow in smooth pipes, lambda 1 is dependent also on Reynolds. Experimentally, there are different kind of flows that can help you to define this friction factor. In particular, Blasius 1, which says that lambda is equal to 8 lambda 1, is also equal to this ratio of a constant 0.316 over Reynolds to the power of 0.25. But the most used laws for determine the friction factor in the condition of transition flow in smooth pipes is, of course, the Prandtl-von Karman. Prandtl-von Karman said that 1 over square friction factor is equal to minus 2 the logarithm of 2.51 over Reynolds times again the square of the friction factor. So basically you can observe that your dependence is given by Reynolds number in the transition flow in smooth pipes, and it's a different dependence from the laminar flow. The problem is that right now we have seen this condition. So let's try to recap what we have seen. Sorry. So we have just seen first case was the laminar flow. For laminar flow we said that the hydraulic gradient J was proportional to the velocity of the flow. And comparing what we got for Darcy-Weisbach to Poiseuille's law coming from Navier-Stokes, we said that first resistance law is that lambda is equal to 64 over Reynolds, where again Reynolds is the density times the velocity of the flow times the diameter of the pipe over the dynamic viscosity. Then, second case that we observed was the completely turbulent flow in smooth pipes that helped us to get Darcy-Weisbach. So it was that J, it was equal to lambda over D times rho to the power of 2 over 2G. The third case was, again, transition flow. So in this case we don't get any resistance law right now. The third case that we have seen right now is the transition flow in smooth pipes where we said that it's valid Prandtl, so this one is it's Prandtl von Karman, and it says that 1 over square lambda is equal to -2 the logarithm of 2.51 over Reynolds times square lambda again. Alright, so dependence on lambda, lambda depends on Reynolds, laminar case. Completely turbulent flow, nothing more to say right now. Transition flow plus smooth pipes, we can say that lambda is dependent from, again, Reynolds number, and that's true, but also from lambda itself. Let's see how can be defined. We have to say that first, right now we have only seen the case of smooth pipes, and smooth pipes are ideal pipes where you do not consider the roughness of your pipe. Basically, what is the roughness? It's like, for example, let's try to write it like this. If you have a circular pipe, let's imagine that is a circle, and these are the wall of your pipe, so your flow is moving right here, the roughness of the pipe is exactly the roughness that you encounter along the wall of your pipe. So it's made by the flow itself, it's made by the materials of your pipe, and something like this. So basically the roughness is something that decreases the diameter of your pipe. Alright, so let's try to go on. Okay, and see what happens if you want to consider the presence of the roughness inside your pipe.